Decarbonization and defossilization represent two interconnected yet distinct strategies in the global effort to combat climate change and transition to a sustainable economy, both centered on humanity's complex relationship with carbon. Carbon, the fourth most abundant element in the universe, is indispensable to life and modern civilization, forming the backbone of organic molecules, materials, and chemicals that underpin everything from biological processes to industrial products. Unlike other elements, carbon's unique ability to form stable, long chains and rings through catenation allows for an astonishing diversity of compounds, over 10 million known organic molecules, making it impossible to simply remove carbon from our lives without dismantling the foundations of biology, technology, and industry. Decarbonization primarily focuses on reducing carbon dioxide, CO2 emissions from energy systems and industrial processes to achieve net zero greenhouse gas levels, while defossilization emphasizes the replacement of fossil-derived carbon sources with renewable alternatives in sectors where carbon is structurally essential, such as chemicals and materials. This distinction is crucial because, while decarbonization targets emissions, defossilization addresses the root dependency on finite fossil resources, ensuring that carbon cycles remain sustainable without depleting geological reserves or exacerbating atmospheric CO2 buildup. As societies grapple with the dual challenges of energy security and environmental preservation, understanding these concepts reveals that carbon is not the enemy, but a critical resource that must be managed wisely. The indispensability of carbon stems from its fundamental role in the chemistry of life and human innovation. In biological systems, carbon is the key element in organic compounds, enabling the formation of carbohydrates, proteins, lipids, and nucleic acids like DNA and RNA, which store and transmit genetic information. Its 4 valence electrons allow it to bond covalently with up to 4 other atoms, creating stable yet versatile structures that facilitate complex biochemical reactions essential for metabolism, growth, and reproduction. Without carbon, life as we know it, carbon-based and reliant on these intricate molecular architectures, would cease to exist. Beyond biology, carbon's importance extends to inorganic and synthetic materials. For instance, in steel production, carbon alloys with iron to enhance strength and durability, forming the backbone of infrastructure like bridges and buildings. In the chemical industry, carbon is the primary building block for polymers such as plastics, which are ubiquitous in packaging, electronics, and medical devices, offering lightweight, flexible, and corrosion-resistant alternatives to metals. Pharmaceuticals, too, rely heavily on carbon frameworks. Most drugs are organic compounds where carbon stability ensures efficacy and safety. Even in advanced technologies, carbon nanotubes and graphene, allotropic forms of carbon, exhibit exceptional conductivity and strength, revolutionizing fields like electronics, energy storage, and nanotechnology. Attempting to eliminate carbon would not only disrupt ecosystems, but also halt industrial progress, as no other element matches its combinatorial prowess. Thus, the narrative of decarbonization must be nuanced. It is not about eradicating carbon, but about curbing its harmful release as CO2 while preserving its utility. Decarbonization, often used as a broad term for climate action, specifically entails the systematic reduction of CO2 and other greenhouse gas emissions across economies to mitigate global warming. Originating from the need to align with the Paris Agreement's goal of limiting temperature rise to 1.55 degrees Celsius, decarbonization targets high-emission sectors like energy production, transportation, and heavy industry, where fossil fuels, coal, oil, and natural gas, dominate. In the energy sector, this involves transitioning from carbon-intensive power generation to renewables such as solar, wind, and hydro, coupled with electrification of end uses like vehicles and heating systems. For example, replacing coal-fired power plants with wind farms eliminates direct CO2 emissions at the source, while battery storage addresses intermittency. Industrial decarbonization might employ carbon capture and storage, CCS, where CO2 from cement or steel production is captured and sequestered underground, preventing atmospheric release. However, decarbonization does not imply a carbon-free world. It focuses on net zero emissions, allowing residual emissions to be offset through natural sinks like forests or technological removals. Challenges include the high upfront costs of renewable infrastructure and the need for grid modernization to handle variable energy inputs. Despite these, decarbonization has proven effective. Countries like Denmark have achieved over 50% renewable electricity through policy incentives and technological innovation, demonstrating that emission reductions can coexist with economic growth. In contrast, defossilization emerges as a complementary strategy, particularly relevant to industries where carbon is an inherent component rather than just an emission byproduct. Defossilization refers to the process of eliminating dependence on fossil-derived carbon feedstocks by substituting them with sustainable, non-fossil alternatives, thereby defossilizing supply chains without removing carbon itself. This term is especially pertinent in the chemical sector, which consumes about 18% of global fossil fuels not for energy, but as raw materials for products like plastics, fertilizers, and solvents. Unlike decarbonization, which might suffice for energy by switching to non-carbon sources like nuclear or renewables, defossilization acknowledges that chemicals require carbon atoms for their molecular structure. Think of polyethylene, where carbon chains provide flexibility and durability. Fossil carbon, extracted from ancient deposits, is finite and its extraction releases CO2, contributing to climate change. Defossilization shifts to renewable carbon sources, biomass from plants and algae, recycled materials from waste, and captured CO2 from the atmosphere or industrial emissions. For instance, bio-based polymers derived from sugarcane or cornstarch maintain carbon's utility while regenerating through photosynthesis, closing the carbon loop. This approach not only reduces emissions but also addresses resource depletion, as fossil reserves are projected to dwindle within decades at current consumption rates. The interplay between decarbonization and defossilization highlights a holistic approach to sustainability, where the former tackles emissions and the latter ensures material continuity. In the chemical industry, for example, decarbonization might involve electrifying processes to cut energy-related emissions, but defossilization is necessary to replace naphtha, a fossil-derived feedstock, with bio-naphtha from vegetable oils. This dual strategy is evident in initiatives like the European Green Deal, which promotes both emission reductions and circular carbon economies. However, defossilization bridges a critical gap. While decarbonization can achieve net zero in energy, industries like pharmaceuticals and plastics cannot decarbonize without ceasing operations, as carbon is integral to their products. Bridging this requires innovations like carbon capture and utilization, CCU, where captured CO2 is converted into methanol or polycarbonates, turning a waste gas into a valuable resource. Such processes exemplify how defossilization supports decarbonization by recycling carbon, potentially achieving negative emissions if sourced from direct air capture. Yet, the distinction is often blurred in public discourse, leading to misconceptions that decarbonization means a carbonless future, which overlooks carbon's irreplaceable role. Delving deeper into defossilization, its methods revolve around three primary sources of renewable carbon: biomass, CO2, and recycling. Biomass leverages nature's carbon cycle, where plants absorb atmospheric CO2 via photosynthesis to form organic matter, which can be harvested sustainably for feedstocks. Second-generation biomass, such as agricultural residues or algae, avoids competition with food crops, yielding bio-oils through pyrolysis or fermentation into ethanol for chemical synthesis. This method defossilizes by regenerating carbon annually, contrasting with fossils' million-year cycles. CO2 utilization, a cornerstone of defossilization, captures emissions and transforms them into products. For example, companies like LanzaTech ferment industrial CO2 into ethanol using microbes, creating a circular pathway. Recycling complements this by repurposing existing carbon in waste plastics through chemical depolymerization, breaking them into monomers for new materials, reducing the need for virgin feedstocks. These approaches ensure carbon remains in use without fossil extraction, but they demand energy, often renewable, to be viable, linking back to decarbonization efforts. The pharmaceutical industry illustrates defossilization's nuances, where over 90% of drugs rely on fossil-derived precursors like benzene or toluene. Defossilizing here involves biosynthesis, using engineered microbes to produce active ingredients from sugars or green chemistry principles to minimize fossil inputs. Similarly, in materials like concrete, Carbon is incorporated via CO2 mineralization, where captured gas reacts with minerals to form stable carbonates, enhancing durability while sequestering emissions. These applications underscore carbon's versatility. Its allotropes, from diamond's hardness to graphite's conductivity, enable tailored properties in composites and electronics. However, defossilization faces hurdles, including scalability. Biomass production requires vast land, potentially clashing with biodiversity, and cost, as renewable processes are often more expensive than fossil ones. Pros of decarbonization include rapid emission cuts, fostering clean energy jobs, and improving air quality. For instance, the UK's decarbonization of power has reduced CO2 by 50% since 1990. Cons involve transition disruptions, like job losses in coal regions, and intermittency of renewables requiring storage solutions. Defossilization's advantages lie in resource security and waste reduction, promoting a circular economy where carbon is reused indefinitely. It preserves industries reliant on carbon, avoiding economic collapse. Drawbacks include potential indirect emissions from biomass harvesting and the energy intensity of CCU, which could undermine benefits if powered by fossils. Challenges in implementing these strategies are multifaceted, encompassing technological, economic, and policy dimensions. Technologically, achieving high-efficiency CCU requires breakthroughs in catalysts and bioreactors, while ensuring biomass sustainability demands certification to prevent deforestation. Economically, the higher costs of renewable carbon, up to 2 to 3 times fossil equivalents, necessitate subsidies and carbon pricing to level the playing field. Policy-wise, frameworks like the U.S. Inflation Reduction Act incentivize CCS and bio-based products, but global coordination is lacking, with developing nations facing barriers to adoption. Socially, equity issues arise, as defossilization could strain agricultural resources in food-insecure regions. Looking ahead, the future of decarbonization and defossilization hinges on integrated policies and innovations. By 2050, the chemical industry could defossilize 50–70% of feedstocks through biomass and CCU, supported by decarbonized energy grids. Emerging technologies like artificial photosynthesis could directly convert CO2 and sunlight into fuels, blurring lines between the two strategies. Ultimately, recognizing carbon's criticality shifts the paradigm from elimination to stewardship, ensuring a sustainable legacy.